And so what this means is that microbiology today is the ultimate in big data science. So, as I mentioned, this is really starting to change our view of ourselves as humans. And I want you to take a moment just to consider what you saw when you looked in the mirror this morning. I saw an organism that was just 43% human, and not just because it was early and I hadn't had my coffee yet. But when we think of what makes us up as humans, when we think about it at the cellular level, each of us has about 30 trillion human cells, but we have about 39 trillion microbial cells, according to the latest estimates. So by that measure, we're about 43% human, as I mentioned. But you might be thinking, well, wait a minute, it's really at the DNA level that we should be thinking about this. So let's think about that for a moment in terms of our DNA. So each of us has about 20,000 human genes, depending on what you count exactly. But amazingly, the size of our microbial gene catalogue is from 2 to 20 million microbial genes, doing the vast majority of unique metabolic reactions in our body. And so by that measure, we're at best 1% human. There's a huge amount of excitement about systems biology, systems medicine, but it's hard to do systems anything when you're ignoring 99% of that system, right? Which is what we do when we ignore the microbial side of ourselves. And you're going to laugh, but this is a simplified diagram of all the ways the microbes in our gut connect to our brain, because you might be thinking, well, what does your gut have to do with your brain, really? And amazingly, your gut microbes are doing all kinds of things, from signaling directly via your nervous system, to releasing neurotransmitters, to releasing small molecule metabolites into your bloodstream that affect your gene expression throughout the body. And just over the last 5 to 10 years, we've learned that gut microbes are involved in all kinds of diseases that we had no idea they were involved in until very recently. One thing that's fascinating about this is these connections between microbes and the mind. And it turns out that even exposure to environmental microbes has a big effect. So we showed last year that you can actually vaccinate mice against an analog of PTSD by inoculating them with just the right soil microbe, Mycobacterium vaccae. And a group in Canada found that you can either make a bold mouse timid or a timid mouse bold by swapping the microbes in their gut while leaving their mouse genes completely unchanged. So these connections are not just correlative, but actually causal. You can change behavior by changing the microbiome. Now, as I mentioned, a lot of this is fairly complex, and a lot of what's been done so far in microbiology has been based around single organisms. So if I ask you to think about a classic gut bacterium, you're probably thinking about this guy, E. coli. And it is true that E. coli is found in the gut of most people, but it tends to be very rare. So if you're healthy, only one cell in about 1 million is going to be E. coli. The rest of it, so it's not a dominant player in that ecosystem. And the reason why we know so much about it is not because it's dominant, but rather because it's great at growing in a petri dish, and it's great in growing in liquid culture. So it's kind of like trying to understand the rainforest by looking at each animal in its cage in the zoo, knowing nothing about its interactions with other species or its interactions with its natural environment. And so to escape this, we have to go to where the microbes are and understand them directly from environmental sampling and reading out their DNA. And the reason why we can do this was really pioneered by Carl Woese, who realized we could use molecular markers to construct a universal tree of life that connects all organisms from any environment. And so we can actually build a network. So this is a network representing hundreds of different environments and showing the unity of life across all of these environments, including the human body, by connecting them with the microbes they share. And so essentially what's going on is each of the different colours represents different kinds of habitats, so free-living habitats versus the gut of humans and other vertebrates, and the skin and so forth. And each of those lines connects a particular environment to the particular microbes that are there. And so this is really amazing because it provides a new way of understanding how our bodies are connected to the planet in microbiological and evolutionary terms. So in the Earth Microbiome Project, which I co-founded, we've now processed about 50,000 samples crowdsourced from scientists around the planet. And what's really exciting about this is that we're getting the first look into how microbes are connected across all of these different environments. And we can use advanced machine learning techniques like artificial neural networks to predict from environmental parameters we can measure what the microbes are going to look like in that environment that they live in. And so, for example, when we apply this in the ocean, this is what we did with Dr. Jack Gilbert at Argo National Labs. from a few dozen surface measurements, we can predict the CO2 that's going to be released over each point in the ocean over a span of years by predicting the microbial community and its metabolic turnover. We can do the same kind of thing in the soil using the Earth Systems model predictions, where from those soil parameters we can predict the microbial communities. So for example, alpha proteobacteria like it dry, and you can see them in the Arctic, you can see them in the Sahara, you'll see them in the Middle East and Australia coming up. We can predict the gene abundance in each of those communities using software we developed called PyTrust. And then we can predict what the CO2 efflux is going to be, and also any other metabolite over the whole Earth's surface under different carbon use scenarios. So we can predict if everyone gave up cars, or if everyone gave up meat, or other things that affect the climate, how would that affect the microbiology, and would it be a positive or negative driver in the climate? We can also apply these techniques on much smaller scales. So this is the office of my good friend and collaborator Peter Dorrestein. We scanned it in a few seconds using a LiDAR scanner, and then what took hours was taking hundreds of cotton swabs and swabbing all the people and all of the surfaces and running them through mass spectrometry to read out the molecules and microbiological sequencing to read out the microbes. And what I'm showing you is one molecule here. You can see that it lights me up very brightly and lights up Larry Smar, our director of CalIT2 very brightly, and Peter's postdoc. He prefers not to be named in this, but not Peter. And the molecule we're looking at is caffeine. You can also see that someone spilled some on Peter's floor in the past. And while this is undoubtedly the most expensive way to find this out, you can see the application, especially if you want to, say, track antibiotics in industrial ecosystems, or understanding what's going on in the NICU. And what's amazing about this is that we can see all different molecules on the people in this office, ranging from common environmental contaminants to the sunscreen on Peter's postdoc, to Larry's meds, to all kinds of other things that come in on the food or beverages that we drink. And we can do the same thing for the microbiology. So you'll notice that Peter is lit up very brightly by Synechococcus. Now, if you know much microbiology, you're probably thinking, well, wait, isn't that a marine microbe? And sure enough, it is. What we're seeing there is that Peter swims in the sea, and he's covered with this marine microbe that he's also transferred to the objects that he touches, again stressing that connection between the environmental and the human microbiology. So in the Human Microbiome Project, this was a large-scale project that I was involved in a number of different capacities. I just got back from the final meeting of the project in NIH, which ended yesterday. And this was a large-scale project where we spent a total of $173 million. The largest single component was a healthy baseline study looking at people at up to 18 sites. The initial paper we published included 242 people. We collected 4.5 trillion bases of DNA, so 1,500 times the size of the human genome in microbial DNA sequencing. And the great thing about this is that we got a tremendous amount of sequence data. That was also the terrible thing about it. So we got 17,000 files just like this. This is the first 0.1% of the file. And it's pretty hard to tell who lives where in the environment from this, right? And the issue is that both through crowdsourced projects like American Gut, which I run, and from various companies, you can now get a profile of your microbiome. And so the problem is, you're going to your doctor and you're saying, hey, I have some great news for you, which is I got 1,000 species that I found in my gut, or 1 million genes that they found in my gut. And can you tell me what's wrong with me in the 15 beautiful minutes we have together? And I mean, what's your good doctor maybe refer you to colleagues in psychiatry for being crazy enough to think that it's going to be useful. And so the goal that we have is to make it not crazy anymore and to integrate that profile with your data over time, the profiles of other people. Just as Dr. Sachs mentioned, we were doing through these various Crook Foundation projects, and as we're doing with many other investigators, to try to understand what those profiles mean. And this is particularly urgent now because over the 20th century, there was this tremendous public health success in the decline of infectious diseases, everything from measles to TB. But at the same time, you see this striking increase in a range of autoimmune diseases, from multiple sclerosis to Crohn's to type 1 diabetes to asthma. What fascinates me is that in 2002, when this was published, none of these diseases were known to be linked to the microbiome, whereas now there's very solid evidence, both from association studies in humans and causal evidence in animal models, that all of them have a strong microbiome component. And my good friend and colleague Marty Glaser has written this wonderful book called Missing Microbes that goes into this in detail. and suggests that some of the microbes that we have lost by trying to be too clean and too sterile may be essential components of our ecosystem that we've co-evolved with that are necessary for maintaining health. And so accordingly, we can actually use the microbiome to do a lot of diagnosis, at least in the context of a research study. And one ongoing challenge is whether we can do this in the context of, in a clinical context where the regulatory framework is very different. But today, for example, I can tell you with 90% accuracy whether you're lean or obese solely by looking at the genes of the bacteria in your gut. So on the one hand, this is pretty cool from a technical standpoint. On the other hand, we don't think it has a lot of commercial potential because as a test for obesity, because I bet you can tell which of these people is obese without doing any sequencing at all, right? But on the other hand, if you try to do that classification task based on human DNA, you can only classify lean from obese with 57% accuracy based on human genes versus 90% accuracy based on microbial ones. And the other thing to consider is that you can't change your human genes, whereas your microbial genes, each of us has changed profoundly from the time we were born up until the present, and we continue to change them by the food we eat, by the people we associate with, by the spaces we inhabit and visit every day of our lives. And if we could take control over that process, there's a tremendous amount of potential. Now, when we think of obesity, it's very clear that the obesity epidemic cannot be caused by human genes, although human genes are obviously involved in response to obesity. And this map from the CDC shows very clearly why. So this is going to start in 1985, showing the spread of obesity across the United States from less than 10% to 10 to 15, 15 to 20, 20 to 25, 25 to 30, and then ultimately over 30% obesity. So by 2010, there wasn't a single state with less than 20% obesity in the entire country. And if that had been a change in human gene frequencies, all the obese people would have had to have had a tremendous number of children, or the lean people would have needed to have been sterile, right? And in either case, we would have noticed. Now, another map that's fascinating to consider is this one, which is the antibiotic prescriptions in 2010, the last year of that obesity map. So notice anything there? If we put it right next to the obesity map, you can see there's a tremendous concordance between antibiotic prescription and obesity. And in fact, the reason why there's so much controversy over feeding antibiotics to livestock is that antibiotics are very effective growth promoters in livestock and fatten them up very effectively. And we may be doing the same thing to ourselves unintentionally by getting rid of beneficial microbes that would keep us healthy and lean. Of course, when we think about obesity, often our thoughts turn less to antibiotics than to food, which also has a tremendous impact. And I really like this quote from Jeff Bland, who likes to say that food is a language that speaks to our genes. In terms of the expression of our genes, how they're turned on and off depends a lot on the food that they eat. And what we're increasingly finding is that the microbiome is the loudspeaker through which the food speaks to our genes. But it's amazing to consider this language, and the language is really the language of color. So all of the different colors in brightly colored fruits and vegetables that you eat translate into chemicals, so whether it's the anthocyanins in the blueberries, or the lycopenoids in the tomatoes, or the carotenoids in the carrots. All of these different molecules are changing how your genes function in your body and how they're interacting with your health. Of course, if you look at brightly coloured foods that are available today, regrettably, this is a store closest to my house in PB where we can buy food. And although my 5-year-old, desperately wants a lot of these brightly coloured items, we're just replacing the natural goodness in all of those foods with synthetic analogues that just don't have the same effect. So when we consider food, there have been some very large epidemiological studies looking at the effects of different foods. And so, for example, this paper in the New England Journal tracked 120,000 people for 20 years, looking at the effect of each individual food item. And so it's probably not going to surprise you to learn which food item is the worst in terms of obesity. And that would be our friend the French fry, which in fact is America's leading source of vitamin C. There's not a lot of vitamin C in each fry, but if you eat a lot of them, which Americans do, you'll get your vitamin C that way. But you also get a lot of things that you don't want, like acrylamide and so on. But for each additional serving of fries that people ate every day over this 20-year span, they gained an average of about 1.7 pounds every year, okay, for a serving of fries per day. Now, what was a bit more surprising is the food most closely associated with weight loss. And the food most closely associated with weight loss as yogurt, right? But again, the effect size is relatively small. So, so for each additional serving of yogurt you eat per day, you lose about 0.8 of a pound. And so what's amazing about this is that every single day for a year, you virtuously forego the fries you were going to eat at lunch and instead have an extra serving of yogurt. Over that whole year, it's only going to be a difference of about 2.5 pounds, which is not very impressive. But this is population average levels, and what you in fact see is tremendously high individual variability, where the same dietary change will have completely large and opposite effects on different people, whether it's for weight gain or for blood glucose response, or for all sorts of other things associated with health. So what's amazing about this is that you can control weight via the microbiome, at least in animal models. So this is what we did with Jeff Gordon's lab at WashU, where we're taking germ-free mice that are raised with no microbes of their own, and when we transfer in microbes from an obese human or from a lean human into genetically identical mice, the mice that get the microbes from the fat human become fat themselves, whereas those that get the microbes from the lean human remain lean. And so we can fairly precisely control how much weight the mice gain or lose by colonizing them with particular microbial strains isolated from people of different body mass. We can also do the same sort of thing for malnutrition. So in a Gates Foundation funded project with Jeff's lab, we did the same sort of thing for malnutrition. So taking germ-free mice, and if they get the microbiome from a kid with kwashiorkor, profound form of nutritional deficiency, the mice do very badly. So they lose 30% of their weight in 3 weeks. They die if they're left untreated. Whereas if they get the microbiome from a healthy twin, if they get the microbiome from a healthy twin, they're basically fine. And what's really exciting about this is it shows that we can pilot nutritional interventions in sets of mice. We can actually rescue the mice that got the quash microbiome by using the same ready-to-use therapeutic food that's used in the clinic in Malawi. And so the idea is that we can pilot therapies, including nutritional therapies, in sets of germ-free mice, and then translate them back into the individual based on the shared microbiological characteristics. So another thing we're really excited about is extending our knowledge of what's actually in food, because despite that long list of chemicals I showed you, if you run a carrot through the mass spec, almost everything you find is going to be a novel compound. Like we can annotate about 3% of the kinds of chemicals we can find in an average piece of food. And so our Vice Chancellor for Health Sciences, David Brenner, recently launched this project to study centenarians in Italy. And one thing that's been especially interesting there is looking at rosemary, where a lot of the herbs that are foraged, so these centenarians are still picking from the wild about 30% of their herbs, including rosemary and thyme and other things that grow wild in the area. And so one thing we've been doing with Peter Dorrestein is taking rosemary, in this case just from the building where we work, and then dividing it up into pieces and using that scanning technique I showed you to highlight the molecules in different parts of the rosemary plant. And so what's cool about this is for the first time we can see where all these different molecules are in the plant. So if you're interested in things like rosmarinic acid, you can see that it's on the old leaves, but not on the new leaves, and that it's fairly concentrated in the flowers. Whereas, for example, methoxycarnosic acid, which has also been implicated in health effects, is mostly in the flowers and not on the rest of the plant. And we also see a huge number of unidentified peaks specific to particular parts of the plant, whether it's the flowers or the stems or whatever. So what we're currently in the process of launching is this project called Global Foodomics. And what we're trying to do with this is just run thousands of samples of food through the mass spec to find what's actually in it. And what you're seeing here is real data. It's a molecular network of how the molecules in thousands of food samples relate to one another. And it's colored by the type of food that we find it in. So you can see some molecules are only in one type of food. So like this is stuff that's mostly from grain, whereas there are other molecules that are mostly in dairy or meats and so on. And almost all of these molecules are unknown at this point, both in terms of their chemical composition and in terms of their function. What's interesting about this is that we see a lot of expected molecules. So for example, piperine from peppers and its various derivatives. We also detect a lot of pesticides. So for example, on the outside of lemons, we see a lot of pesticides that are applied to them that fortunately we don't see on the inside of the fruit. And what we're doing at the moment is we're intersecting Global Foodomics with the American Gut Project. which, if you're interested in getting your microbiome read out, is something that you can sign up for online. It's kind of like National Geographic's Genographic project, where it's a science project to find out about microbiomes where each participant covers the cost of participating. But the idea is that in global foodomics we can figure out what's going in. With the American Gut Project we can figure out what's going out, and then we can combine the analysis of those populations. We ran through about 3,000 people already, and what we're seeing is remarkable. So this is just the intersection between the American Gut Project and what we're seeing in food. And so we can start to figure out which of these molecules are being transformed as they go through the body and what's happening exactly. And so these are some small parts of that network, showing, for example, alkaloids from peppers, showing rosmarinic acid from rosemary, and showing various other derivatives. So, for example, we see a lot of caffeine coming out in the stool, but then theobromine is metabolized by the body, and we see it in the input food, but not in the stool itself. So the final direction we're taking this is, in order to really understand what's going on, we need to get into the body itself. This is something we can't do in humans, but we can do in animal models. This is in collaboration with Peter and with Sarkis Mazmanian at Caltech, where we're taking germ-free and conventionally raised mice and scanning them in the MRI and then dissecting them and looking at each organ, which we can reconstruct in 3D, and ask what molecules and what microbes are in each organ. So when we do this, we can essentially look at where any kind of bacterium is in the whole mouse when we reconstruct it. And when we look at the metabolites, what we can do is we can link those to each other. So for example, if you look at something like soya saponin, which comes in on soy, it accumulates, so that's these red areas in germ-free mice, but it's gone in the conventional mice that have all their microbes. Whereas you can see that its metabolic breakdown product, soya sponginol, is only produced by microbes, so it's only in the regular mouse and not in the germ-free one. So you might be wondering, well, should you actually care about this, or is it just some cool trick we can do in the lab? And the reason why you should care, so this just came out in Science last week, but one reason you should care is that the food that you eat has a tremendous impact on, for example, whether you're susceptible to the flu. So this is from Tad Steppenbach's lab at WashU, and what they found is that when you take normal mice and you expose them to flu, about half of them die. If you give them antibiotics first to wipe out their gut microbiome, 95% of them die. Okay, if you give them antibiotics and then you restore one of the beneficial microbes out of the gut, only 25% of them die, so half the number that would die if they're untreated. And then the reason why is that what this microbe is doing is it's taking a normal product of plant secondary metabolism and it's changing it into this compound called desaminotyrosine. And when you just administer high levels of desaminotyrosine to mice, only 5% of them die, so it's essentially completely protective against flu. And so what's really exciting about this is that the intersection of what you eat and what microbes you have in your gut likely determines not just the impact of chronic disease, as you've heard so much about already, but also the impact of acute infectious disease, and can keep you healthy over a lifetime from that as well. One thing that Tad talked about at the conference last week, but did not put in this paper, is that the same sort of thing is true for a high-fat, high-sugar diet. So if you keep the mice on a high-fat, high-sugar diet and don't feed them the plant precursor that it can make this molecule out of, they also die at very high mortality rates. So both what you eat and what microbes you have are critically important. Now, so what this may mean is that we may need to rethink what compounds of food we should really care about, and also think about resupplying microbes as well as resupplying compounds. But supplementing food to make it healthier is something that's not a new concept at all, even for things that you wouldn't necessarily think of, even for things that you wouldn't necessarily think of unless you knew the answer already, as being linked to the gut. So, for example, goiter, and then in a more severe form, cretinism, which was a profound form of mental retardation, used to affect millions of people, but they were essentially completely eliminated by the simple method of iodizing salt, despite the fact that you have a very complex developmental and cognitive phenotype. You can completely eliminate that phenotype with a simple dietary supplement. And so what we're trying to figure out is, are there other simple supplements like that you can isolate from food, or better probiotics that you can isolate from the gut, in order to make the kinds of discoveries that would lead to this kind of thing, that could provide resistance against flu, that could provide resistance against autism based on Sarkis Mazmanian's work, and provide resistance to all kinds of diseases that we currently think of as being as chronic and as incurable as goiter and cretinism we thought of a century ago. So I'm just wrapping up now. So you might think that this is pretty implausible, especially the idea that we might be able to do it in the developing world. But technology penetrates out the planet at a remarkable rate these days. And for example, Tandu Yatseneko, one of Jet's grad students, took this photo in Malawi in 2009 at the malnutrition clinic, where although food is scarce, you'll notice that cell phones were available. And the amazing fact is that there are over 7 billion cell phones active on Earth now, more than one for every person. And this is true not just in Malawi, but everywhere. So I took this photo in 2012 in Bangladesh, in downtown Dhaka, where next to a sizable hunk of a cow, you can get your cell minutes recharged. And perhaps most remarkable, in 2014, I was working with the Hadza hunter-gatherers in Tanzania. And so I had the pleasure of shaking hands with a man who a couple of weeks before had shot a giraffe with a bow and arrow that he made himself and traded the meat and some of the hide of that giraffe to the Datoga, the next group over, for the cell phone that he's holding here. And he keeps the electricity minutes topped up by literally gathering honey and trading it for electricity in minutes, right? So the reason why this is possible is that the cost of cell technology has been dropping precipitously because the digital signal processing you need to set up a cell network is so cheap it's basically free. But something that's getting cheap even faster is DNA sequencing. And the value of this technology, if we can make it robust and easy to use, it's the kind of thing that we believe will penetrate everywhere. Because valuable as communication is, understanding the basis for your own body's health, we would argue is even more valuable than that. So I'll end there. I hope you've been inspired to think in new ways about the connections between your body, your mind, your food, and the world. And I'd be delighted to take any questions at this time. Thank you.